Hello. In this video we're going to be talking about topological ordering of graphs, and this is not a difficult concept. It is very similar to it is identical to the prerequisite ordering of courses. So let's just get started with it. In a general graph you can also put things in a topological order if it has a certain characteristic. So here's the mathematics of it. Topological ordering is a linear ordering of the vertices, so that if f v sub ij is a predecessor of v sub ik, then v sub ij precedes v sub ik. So we have to assume that the graph has no cycles, because it would be catch-22 situation if we said you have to take 203 before you take 204, and you have to take 204 before you take 203, or something silly like that. So we have to assume that the graph has a first vertex and a last vertex, which is true if it has no cycles. So here's what you do. First you create an array predecessor count and initialize it so that it's the number of predecessors of vertex v, and then initialize the queue to all those vertices v that pred count is 0. So the queue is not empty because the graph has no cycles. So here's the third step. While the queue is not empty, move the first element, put it in the next available position, and then decrement the predecessor count by 1. So here's an example. Let's say we have this graph. It has no cycles, so you know that node 0 and actually node 9 also have no predecessors. Also, it turns out node 10 has no successors. That's mathematically guaranteed by the fact that it has no cycles. So the first thing we do is count the number of predecessors. So let's do that, and we see in predecessor count that we've counted the predecessors, and in some cases there's 0 for 0 and 9. Node 0 has no predecessors. Node 9 has no predecessors. The others have between 1 and 3, but that doesn't really matter for now. So we take the first two, the ones that are 0 predecessor, that's step 2 up here, and we remove them from the graph, and put the name of the node, of the vertex, in the queue. And then repeat 1 and 2 until the graph is empty. So let's see how that works. We delete 0, delete 9, because there's 0 predecessors. And then we recount. Now anything that's 0, we just mark it as a dash, just to make sure that we don't recount it. So there's the two that are we've removed from the graph. And then we recount the predecessors. Now you'll notice that node 1 has 0 predecessors, and node 3 see, there's another one. Oh, we need to go all the way down the list. Node 7 has no predecessors. It used to have node 9, and so we've recounted, and now node 1 and node 7 have 0 predecessors, so we take them off the graph. We basically do step 2. We remove them from the graph, 1 and 7, and put them in the queue. There they are. Now we do the same thing. Now node 2 and node 5 have 0 predecessors, but first we have to 0 out the 1 and 7, or dash it out, remove it from the list. Now we recount, and nodes 2 and 5 now have have 0 predecessors. So we put them in the queue. Repeat 4 and 6. Put them in the queue. Repeat for 3 and 8. And now node 10 is the only one that has no predecessor, so we put it in the queue. And then when we're done with the queue, we can dequeue the queue and put them in the topological ordering. Now, some places it says every time you put them in the queue, then you enqueue them and then you immediately dequeue them. Either way, works out the same either way. So here's another graph, slightly different, to show the pred count, the topological ordering, and the queue. This is what makes a lot of sense to us. This is the prerequisite chart for a number of languages, not the same as Montgomery College, of course, because we don't have all these 300 and 400 level courses. But this is a prerequisite, a topological ordering. You have to start at the beginning, and you can do discrete math, which is 207, and programming 1, which is 203. But at this college, you have to have both of those done before you can move on to programming 2. But for computer organization, you don't have to have discrete math done. So that is topological ordering, and now you're equipped to do the last 2 pages of the graph lab.